Good afternoon. This is Schweitzer, and this is going to be, looks like our last video before our quiz. Again, our main topic here is, for this quiz, is basically what is K, how does equilibrium work, and what are our basic type of calculations we need to be handling here. Solubility is one of the big ones. Specific types of actual calculations. So we're going to just take a quick moment and look at this particular one here and get you more familiar with that type of chemical reaction. So silver chloride is dropped into a beaker of water. The silver chloride starts to build up at the bottom right out the reaction that's taking place. Okay, so silver chloride is being dropped into a beaker. So all we have here is essentially we're dropping solid silver chloride into AgCl in here, and it starts to dissolve, form Ag plus and Cl negative, Ag plus Cl negative, and eventually gets saturated and it fills up and falls to the bottom like this, AgCl. So write the reaction taking up place here. Well, it looks like we got Ag plus Cl minus yields AgCl. Now this reaction could also be written as AgCl comes from Ag plus Cl minus. Now typically your average chemistry student would probably write it like that. But in this chapter, we'll probably hopefully see in a little while, is we're going to use this version. Neither one's better than the other one, but we typically use this one here. So let's write out their expression. K, again, I'm going to use Kc. Okay, now this one here, this particular version here, okay, not that one, this one, has a special name called solubility product. Product just means multiplying. So you'll see why they call it Ksp. Now again, don't be afraid of that little Sp there. It's just telling you the type of reaction that's taking place. It's telling you that it's this one, not that one. Which is going to be products over reactants. And of course, I don't have any products. They're solid. One, Ag plus, and Cl minus. You'll note that these concentrations are the same in my beaker, one each, because of how they're being distributed in the formula at one each. Alright, so how do the concentrations of the ions compare? Well, so the ions, okay, their concentrations I just mentioned are equal. It isn't always that way, but typically they could be equal, or one could be twice that. It depends on what you're dissolving and the stoichiometric ratios of the items present. Alright. Alright. So for each of these guys, now one thing I'm going to just quickly mention here, just so you know, I don't know if it'll be later on, but one thing I'll mention here is that one reason why we use this particular equation is because as solubilities increase, now this guy right here, okay, a couple things you want to note about that for Ksp. One is that in order, it's not referring to this dissolving process. That's not what this reaction is talking about. What this reaction is talking about is this process down below, which is that this guy now dissolves back out, and this guy returns here. This right here is the equilibrium process, not up top. This is where the stalemate is concerned, and that is what sometimes causes problems. So what's going on here is that, first of all, if you have solid on the bottom, okay, then you know that you are at the max solubility. You cannot dissolve anymore. And that is kind of a key idea to be having this going back and forth. If this wasn't at max solubility, then your dissolving rate would be bigger than your precipitation rate, and you wouldn't be at equilibrium. You'd still be gaining concentrations. We want to reiterate this process never stops. It keeps going back and forth for eternity. It's just that we have to have both present in order for this to occur, and this has to be at maximum solubility, maximum holding capacity. So at stalemate or at equilibrium, then these concentrations are not changing. They're the same because of the fact that we're at stalemate now. So one thing we call these things, these concentrations here, are called molar solubility. That's a new term that we're going to use, and it's basically the maximum solubility in moles per liter. Alright, so the next thing we got to kind of have here is that because we use this formula, the reason why they use it. Now, people in industry, they use this thing purely for a reason, because they needed it. They used it. And they wanted a K value that correlated proportionally to molar solubility. This will likely be covered again. But when you use this equation, as these go up, so does this. These two correlate. Okay? I'm not saying that because different dissolving substances might have different algorithms. I mean, they have some squares here, some. You can't necessarily compare one item's K to another item's K unless they have the same algorithm. But in general, larger Ks yield larger solubilities. If we use the reverse reaction, then the K would be reciprocal. This reaction, larger Ks would be correlated to lower solubilities, and people just didn't like that. So they decided to use this version of the reaction, and there we go. What does this thing look like? Well, as they start dissolving, we just start with nothing, and the Ag and Cl will take the same path, and it just levels off. At that point, we've sort of reached equilibrium right about here, and this is the Ag plus ion and the chloride ions in solution. Alright, so let's go ahead and try out some of these. Rank these in order of increasing solubility. Now, as I mentioned, if you have the same expression, then you can use the same solubilities. Okay, now, another thing you might note is our KSPs are very small. Again, this correlates to solubility. So we are only using things that are very, very slightly soluble in these situations for KSP. Expression, so it's going to be PbSO4 comes from Pb2 plus SO4 minus 2. The KSP equals the concentration of Pb2 plus concentration of SO4 minus 2. This guy is BaSO4 goes to Ba plus 2 plus SO4. You should be trying this on your own. I always forget to say that, but you should always be. Alright, pause it, try the next one. We just go concentration of Ba plus 2, concentration of SO4 minus 2. Make sure you keep your charges on there. No, nothing here yet. And this we got here, PbCl2 goes to Pb2 plus. So now here's a little different one. 2Cl negative. So it's going to be Ksp equals concentration of Pb2 plus times the concentration of Cl negative 1. And this one's going to be squared. Alright. In this case, so rank the solubilities. Well, first of all, these numbers could be something here. Okay, I can directly compare these two. All right, because they have the same algorithm, I can say that this guy's smaller, so this guy's more soluble than this one is. I might be able to make the assumption that that this guy is way smaller, 1,000 times smaller than that one. So maybe barium sulfate is at the bottom. These two might be a little harder to do because they have similar K values, but they're using different algorithms. I've never seen an AP question ask you to do this. Only time they've actually compared these is if they have all the same algorithm. Then you can just compare the K, which is nice. Let's take a moment here and let's see what the actual answers are. I'm going to add a new page in here and we can calculate the actual solubilities. We'll see this. This comes off the last chapter quiz, so it can sometimes be on the. It's just a calculation. So let's do this guy first, and we'll do this guy second. So 1.3e to the negative fifth. So it's PbSO4 goes to Pb2 plus SO4 minus 2, initial stoichiometric ratio, and this is not playing a role. It's a solid. I have none of this to begin with, so I'm just pouring it into empty water. Again, as I pour it into empty water, this is 0. I'm going to get 1 lead and 1 sulfate. Okay? There we go. There we go. We got plus X, X, and X. So at this point, we're calculating this out. The Ksp equals the X times X, and that's just equals X squared. So my K value once again is 1.3 -6th. Alright, so it's 1.3 e to the -6th, and I just got to divide it out. Square root it out. 1.3 e to the -6th. We'll square root that value, and I get .x equals 0.00114 with 3 sig figs. Alright, let's do the last one here. I'm going to get 1.65. Alright, so it's going to be PbCl2 goes to Pb2 plus Cl minus, 2 of them. Initial stoichiometric ratio n, not playing a role, 0, 0 plus x. Now this one I'm going to gain 2x of that guy. My beaker would have Pb2 plus and 2 Cl minuses. Alright, so plus x, so this is x and this is 2x. Alright, so Ksp equals concentration of Pb2 plus times the concentration of Cl minus. Alright, and then we're going to get x, plug these guys in here. Okay, so we're seeing our first solubility type processes. These guys get plugged in. X and 2x, and this guy is squared. So we're going to get the Ksp value, which is 1.6 e to the -5th. Alright, 1.6 e to the -5th equals x times. Now when I square this thing, I get 4x squared. 4x squared. And then I get, this guy is 4x cubed. Pay careful attention to the algebra here. Divide the 4 out and then cube root. So to 1.6 e to the -5th divide by 4 raised to a power of 1/3. Okay, 1.6 e to the -5th divided by 4, and then raise, I use the caret, to 1 divided by 3 in parentheses to the caret, and I get an error. You could do 0.333 if you wanted to. And I got 0.0158. So 0.0158 moles per liter. So who's more soluble? Looks like this guy's much larger. So go back here to my original page here, and we'll go with, let's say, in this situation here, rank in solubility. So this guy is going to be last. The PB, this will be second. This will be, let's do it this way, number 1, number 2, and number 3. I calculated that solubility, and I calculated this one. We didn't do this one. Okay. So I want to stop the video here. Our first example of just looking at KSPs, how they work. The video's long enough at this point. In our first calculations for how to solve for a molar solubility. Keep in mind, in this point, when I did my calculation, this X is the molar solubility. It's the amount that actually dissolves. It's a 1-to-1 ratio to that guy. So that's how much, that is the answer. If you want to know the molar solubility, it's X. Of course, that represents this guy at 1-to-1. What's the concentration of lead ions? Same as this. What's the concentration of chloride ions? Double. Okay. Alright, I think we'll stop there. Thank you.